I recently stumbled upon this fascinating physics term, the terahertz gap. It sounds kind of empty, doesn't it?
Huh, it definitely does. And for decades, it basically was empty for practical use. We're
Okay.
talking that frequency range,
hmm
100 gigahertz up to maybe 10 terahertz.
Right, that bit of the spectrum.
Yeah, and it was this awkward spot stuck right between traditional electronics, microwaves, and then photonics or
Hmm.
optics dealing with infrared and light. Neither technology really felt at home there.
Okay, so why not? What was the roadblock?
Well, two main things. With electronics, you hit this fundamental limit. Uh, think above maybe 300 gigahertz. The electrons in the circuits, they literally can't switch fast enough to
Yeah.
keep up. It's called transit time roll-off.
Too slow for the signal. Got it.
Exactly. And then if you tried coming at it from the optic side,
Uh-huh.
well, terahertz photons, they have really low energy, tiny energy.
Meaning?
Meaning they just get drowned out by background heat, thermal noises, especially if you're trying to detect them at room temperature. You basically couldn't see the signal.
So this deep dive, our mission really is to explore how we're finally cracking this. I hear terahertz photonics is the key phrase now.
That's the one. It's about blending optical ideas with semiconductor tech
Mhm.
to finally tame this frequency range. And it's opening doors for some pretty amazing applications.
All right, let's dig into that. If the old electronics were too slow, how does this photonic approach actually generate or, detect these super high frequencies?
A key technique is something called continuous wave photomixing. It sounds complex, but the idea is actually pretty neat. Instead of slow electrons, use light.
Okay.
You take two laser beams, infrared usually, slightly different frequencies, and you mix them together on a special kind of semiconductor antenna.
Like smashing them together?
Sort of, yeah. And that mixing process generates a new wave, and its frequency is the difference between the two original lasers. And that difference, it falls right smack in the terahertz band.
Ah, so you sidestep the electron speed limit entirely.
Precisely. You're generating the terahertz wave directly using light interactions.
And performance-wise, what does that buy us?
Oh, it's a huge difference. We're now seeing dynamic ranges hitting, well, easily over 90 dBs per root hertz at 1 terahertz.
Okay, translate that for us. 90 dB, that means.
It means the signal is incredibly clean. You can detect really faint terahertz signals clearly above the background noise. Just a few years back, you needed, complex, cryogenically cooled lab setups to even get close to that. Now we can do it at room temp.
Wow. Okay, so with that kind of signal clarity, what can we actually do? Sensing sounds like an obvious first stop.
Absolutely. This enables what we call terahertz fingerprinting. Many molecules, especially gases, have unique ways they rotate or vibrate, and these leave specific absorption lines, like fingerprints, in the terahertz spectrum.
Fingerprints invisible to other types of light.
Often, yes. Or at least much clearer in the terahertz range.
Mm-hmm.
We can even achieve isotopolog sensitivity.
Meaning you can tell the difference between isotopes, like slightly different versions of the same molecule.
Exactly. Which is huge for things like trace gas detection in, say, astronomy, or even analyzing breath for medical diagnostics. Tiny amounts, very specific molecules.
It's incredibly precise. Okay, shifting gears to industry, non-destructive testing, NDT. How does terahertz fit in there? Better than X-rays or ultrasound?
Well, a couple of big advantages. First, it's non-ionizing radiation. Totally safe for materials and people, unlike X-rays.
That's a big plus.
Huge. And second, it penetrates many non-metallic materials that visible light just bounces off or that ultrasound struggles with. Think plastics, ceramics, paint layers, foams, clothing.
Okay, I can see applications there, like quality control.
Definitely. For instance, in the car industry, tiered set systems are actually deployed on the production line right now. They monitor the thickness of those multi-layer paint jobs in real time.
To what accuracy?
Talking sub-micrometer accuracy, it's incredible. And historically, remember the space shuttle. Terahertz was critical for checking the external fuel tank's foam insulation for hidden voids or defects. Can't get much more critical than that.
No kidding. Safety and penetration. But I hear the really big buzz is around communications, the 6G future.
Oh yeah, that's potentially the killer app. We all want faster data, right? The Shannon-Hartley law tells us basically if you want more data per second, you need more bandwidth.
More highway lanes for the data.
Exactly. And the terahertz band, it has enormous stretches of unused bandwidth, just vast amounts compared to what current Wi-Fi or 5G use.
So the goal is terabit per second speeds, TVPS.
That's the target. And people are already showing it's possible. There have been demonstrations. I think one showed over 1 terabit per second transmission over 100 meters using photonics-assisted systems around 300 gigahertz.
Wow. But there must be challenges, right? It can't be that easy.
No, physics always gets a vote. The main issue is path loss. Terahertz signals attenuate really quickly in air, much more than microwaves. And they don't bend around corners well. They act more like light beams.
So short range, and you need line of sight.
Pretty much. Which means you need really focused directional beams and technologies like ISAC integrated sensing and communication.
ISAC, what's that?
It's clever. It means the same signal beam is used for both sending data and sensing where the user or device is located, so the beam can track them precisely. It has to be dynamic.
Okay, managing those beams, the tracking, the data, that sounds like it needs some serious smarts behind the scenes, a lot of complex control.
It absolutely does. Sophisticated algorithms, real-time adjustments.
Yeah.
That's where AI and advanced software come in.
Right, which actually connects really well to our sponsor for this deep dive, Silk. If your business is looking at complex systems, maybe AI training, automation, or figuring out where intelligent software agents could really boost efficiency or create new possibilities, you should check them out.
Good point. That kind of intelligence is crucial for making these advanced tier systems practical.
Find out more at embersilk.com. So looking forward then, what's the next big step to making Terahertz truly mainstream?
Miniaturization is key. All this amazing performance we've talked about used to take up an entire lab bench.
Right. Big, clunky equipment.
Exactly.
Yeah.
Now we're integrating these components onto tiny chips, photonic integrated circuits, or PICs. Think computer chips, but for light.
So combining the electronics and the photonics onto one tiny platform.
That's the vision. And it means high-performance terahertz systems, small enough to fit on your thumbnail, are genuinely becoming foreseeable, not science fiction anymore.
That really feels like we're closing the book on the terahertz gap for good. It's not a gap, it's becoming a tool.
A very powerful tool.
The provocative thought here isn't just faster downloads. It's systems that can see inside materials with incredible detail, identify substances instantly, and communicate at lightning speed, all potentially from a tiny device.
It really could change how devices interact with the physical world around them. A fundamental shift.
Absolutely fascinating stuff. If you enjoyed this deep dive into the world of terahertz photonics, please do subscribe to the show.
It helps others find us.
And hey, if you have a moment, maybe leave us a 5-star review. It genuinely helps get the word out about these topics. Thanks so much for tuning in.